are starting off with our, which lab is this? Lab number 5, right?
Yeah.
And this is a free fall experiment. So basically what we are trying to do is to let something fall freely, and by knowing the height of fall and the time of fall, we can actually use the equations of motion and find out the acceleration due to gravity. That is what we're going to do. So we're going to find the acceleration due to gravity. So what is going to be our title? Acceleration of free fall. That's going to be our title. Acceleration of free fall. And our aim is to determine the acceleration due to gravity in the lab. Using the free fall apparatus. And what is our materials required? You need a stand. You need the free fall apparatus, which consists of a very precise timer, digital timer, that works sometimes. A very precise digital timer, a ball release mechanism. This is a ball release mechanism. That's a ball release mechanism. It's got a screw on the top. So we take the ball and fix it in that space over there, which electrically completes a circuit. Ball is made of steel. So it electrically completes a circuit, and this is wired into the timer. So this is a ball release mechanism. How do you release it? Just unscrew it from the top, and immediately the ball gets released. And the ball starts falling from initial velocity equal to 0, right? That's why. Because it's hard to drop something and also start a timer. Like you're going to start a stopwatch with your hands by seeing it fall. That's going to be totally inaccurate. So this one is going to be very accurate because it's a digital timer and it is connected electrically. So as soon as the electricity is lost, like as soon as I release the ball, electricity is lost and the timer starts running. And this timer is more special because it actually can give you the precision of this one is like 10,000th of a second. What's the precision of your cell phone stopwatch? 100th. So this is not 100th. It is not even 1,000th, but 1/10,000th. So this can give you an answer. Right now you can see what is displaying here. Like 1.44501 seconds. 1.4501 seconds. See how many 4 decimal places. That's why this is expensive. And that's why it's very delicate too. I mean, like it can sometimes work, sometimes won't work properly. And all right. This is expensive. This gadget is expensive. I wish my school bought some of these. They're expensive in this way. Okay. So I try to do it by other ways. There are so many other ways of doing it, as a lab activity. All right, so this is a very precise, that's what I'm trying to say. The digital timer is very precise. So as soon as the ball gets detached from here, the timer will start running, and the ball is falling, and then it falls onto a pressure pad switch. This is a pressure pad switch. It's a pad, and it's got a pressure sensor there. So as soon as the ball comes and hits like that, the timer freezes. So as soon as the ball comes and hits the pressure pad switch, the timer will freeze, giving us the actual time of fall from the time the ball got released till the time it actually hit the pit. So we are not actually going to do any timing. Whatever it says, that's what we're going to take. But we won't take it for granted always. We'll just try to repeat it and repeat it just to make sure that it is actually right answer. But sometimes what happens is when you release this ball, the ball can gradually start sliding, and the electricity is probably not lost yet, so which means that errors can creep in. And just to avoid those errors, we kind of repeat it 3 times. And if they are very near to each other, supposed to be very near to each other, and if they are very near to each other, we take those 3 and take an average. Okay, so again, we need to do, even though it's an instrument, I don't want to trust the instrument straight away. So we have to just do it 3 times, take an average on that one, because there are a lot of mechanical errors that can come in this experiment, like how quickly am I releasing this knob, such things. Okay. All right. So the materials required: the free fall apparatus, which consists of a digital timer, a ball release mechanism, a pressure pad switch, and a steel ball. That's all you need for this experiment, and a meter stick. You need a meter stick to measure the heights. The formula, so theory. Theory of this experiment is pretty much the same as your the theories that you have done in your lecture. When something is released from somewhere, it falls through a height. Now, how do you measure the height of fall? From where to where? From where to where do we measure the height of fall? This is the pressure pad switch, and that's the steel ball. So where to where should I measure the height of fall? The ball is going to fall. From the center of the ball to the table, to the pressure pad switch. Is that right? So I'm going to show you some experiment here. I'm going to drop this. Tell me how much distance it actually fell. Now, if you say from the center of this thing to here, watch. How much did it fall? From the bottom to the top here. You get it? Not from the center. So the height is going to be measured from here, from the bottom of the ball to the height. So basically that's going to be the height. That's the height of fall. So we need a meter stick to measure that. Can you pull the second drawer down there, the bottom here? I suppose there are meter sticks there. Are there? Yeah. Can you bring one? So that is that's a height of fall, And then your digital timer gets you the time. So we have the height, we have the time. And let's use the equations of motion. What's the equations of motion? Vi is equal to 0, right? Initial velocity is 0. So we know that. We know this. And what we don't know is the acceleration. This is what we are trying to find out. Acceleration to gravity. So tell me an equation which connects all this. You should be really good at it now because your test is in process too. Yeah. What is the equation of motion that connects initial velocity, displacement, acceleration, and time? Something that does not have final velocity. What is that? That's equal to what? We don't want final velocity. I'm not interested. We want to connect these. I don't want an equation with the final velocity. So tell me an equation without final velocity.
V equals initial velocity times time plus 1 half.
Initial velocity times time plus 1/2 acceleration times v squared. That is right. But the d is the distance followed. In this case, it's the height. Right? Now understand that this height actually, when it falls from here to here, it's a negative displacement. It's going to be negative displacement. So also acceleration is negative downward. So I'm going to ignore the negative concept right now. So let's take it as just height. And that is 0, right? Because initial velocity is 0, that part is 0. So all you have is 1/2. Acceleration is the acceleration to the gravity, which is g. That's what you're trying to find out. And then the c squared. So that is the theory behind it. Our equations of motion is going to help us to do this experiment. Now if I multiply through it by 2, I get 2h is equal to gt squared. So if I actually divide both sides by t squared, I get g is equal to 2h over t squared. And as I said in the previous experiment, we are not going to do the experiment with only one piece of information, one height and one time. We'll repeat it for 5 different heights. Just like the pendulum, we did 5 different trials, 5 different lengths of string. Same way here. We're going to repeat it for 5 different heights. And so we are going to plot a graph of height versus t squared. Pretty much similar to the last experiment. Very similar. Now you know how to draw a graph, right? Okay. From the last experiment. I'm going to go over it now. We're going to plot it right now. So obviously when you finish the experiment, you will get a set of points like that. And you draw the best fit line. And then you get the equation for that line, y equal to mx plus b, where this m stands for the slope, and that's what you need. That slope is what goes in here. So what is going to be our final answer? The final answer is 2 times the slope. So our calculation is going to be so easy. Whatever, 2 times the slope, that is going to be a final answer. So, where are we right now in the lab report? I told you about the theory, and this is all the theory behind it. You can take an actual picture of the graph, setup to add to your lab report if you want, or you can draw one like this. It's fine. And the theory will be talking about the equations of motion that's connected to this falling object, and then the theory also will finally end up with the formula. So the formula required will come here. So theory and formula required, you can put them together. So that is what we're going to do. This is a quick experiment. You should be able to finish it soon. I can finish it. If you want, you can also do that parallel to it.
So when you write it in the theory and the formula together?
Yeah, you can put it together.
Okay.
Theory and formula, as long as you're writing the formula and the theory, it's all built into the lab report. I'm not going to be hard and fast on, no, we didn't split the theory and the formula required. No, you don't have to. If you can club them together and write it down as a good lab report, that's fine. Right? So the thing is, like, if you just title it as theory and formula required, and then you can say anything about the formula, then that's wrong. So you need to show the theory behind it, which is talk about the equations of motion and how this actually works, and finally the formula required. You can also mention about the graph that we use. Why do we draw a graph? We draw a graph to take better averages and therefore reduce the sources of error, which is how you can get more accurate answers. So the graph actually helps you to get more accurate answers, and the graph also helps us to eliminate some errors. such as if someone thought the height is going to be measured from the top of the ball by mistake. It's a mistake. But it's not a costly mistake because when you draw the graph, all the numbers here are going to be scooted up because it's higher. So still the graph will look exactly the same, the slope will never change. The slope won't change. You will definitely get an intercept, which apparently is a mistake. So if you don't make a mistake at all, this number is technically supposed to be 0. If all the readings are perfectly alright. Now, if you see some number over here and it's like significantly big, whatever is here is the distance, is the height in meters that you went wrong with. It's not necessarily just the height, it also can depend on the time. If the times are thrown up and down, you can still have issues. Alright? So, what we have next is a procedure, which is simple. What is the procedure? What I'm going to do, this is the steps. I first place the ball into the ball release mechanism, and then I reset the timer. So the timer reads 0, 0, 0, 0, 0. And then I measure the height, which is from the pressure pad switch to the bottom of the ball. In this case, it is 32 point. 32.7. 32.7. So the height is 32.7 centimeters. Okay, so let me now remove this and make our table. So what is the table that you're going to do? Height in meters. Time 1, time 2, and time 3, time of fall. In seconds. So we have 3 times. Average time in seconds. And then time squared in seconds squared. That's all we need. So what did I say our first height is? 32.7, so 0.327 is going to be our first number. Since I already put meters over here, you don't have to put units everywhere. So, steps are this. Place the steel ball into the ball release mechanism. Reset the timer. Place the pressure pad switch right under the ball so that it lands on the pressure pad switch. And then we make sure that the stand is not going to wobble. So hold the stand firm and quickly release this mechanism, very quickly. And I have a time here which is 0.2598. So can you write it down somewhere so that I'm not saying that is the right answer, but 0.2598 seconds is what it says. 0.2598 seconds. So just keep in mind, write it somewhere. I'm going to repeat this experiment again. So there's a kind of spring loading here to load this. And then reset it. So release quickly as possible. And timer did not work. So that will happen always. Again, I load it. Reset. Quick release. 0.2580 seconds. 0.2580 seconds. That looks right. I'm trying again a third time. If this also comes out pretty close, then I'll stick with it. 0.2588. 0.2588, and they all look good. 0.25 I don't know what the first was, 0.2598 I think, 0.2580 was it? And then 0.2588, can you take the average of that and put it here? Put those three numbers here, and then take the average and put it here. Can you say that loud so that those who are watching the video can also get the average and confirm that they're also doing it right? So 0.2598 plus 0.2580 plus 0.2588 equal to, divide by 3, equal to, what's it? 0.2589. Okay, 0.2589, write it down as the average time. And then square that, 0.2589, like enter it separately on the calculator. Don't use the previous average. 0.2589 squared. And what do you have?
0.067.
0.067. I need four sig figs.
0.
0, 0,
No, just
0.0670.
2. What's the next digit? Oh, so 3.
Right.
You need to round it. So 0.06729 becomes 0.60673. Okay, so we got it all. So we are not losing any significant digits as it is. So this is your square. So you know the procedure now? What the procedure is? And then what do I do next? I just scoot this up to a different height. And I repeat the process. And I'm going to do it. So you're going to take the readings, reset the timer, and then measure the height. Forty-one point 41.8. 41.8, so it becomes 0.418 meters. I reset the timer, and I'm going to release it. I'll hold it here and release. I've got a time of 0.2902. Can you write down 0.2902? And then repeat. Reset. Wrong time. Repeat. Reset. Wrong time again. Wrong time. Point 2910. What was the previous one? Okay, 0.2910. That looks good. All right, we'll do it one more time. Wrong time. Point 2899. That also looks good. 0.2899. So now you can take the average, do exactly what you did earlier, round it up properly to 4 sig figs, and then get me the answer. So is it 0.282905? No, 04. 0.2904. Okay, write it down. and then square it. Let's put that down there. 0.084 33. Everyone's agreeing with it? What? Oh. We have 0.2902, 0.2910, and 0.2899. Yeah, it is right. 0.2902 is correct. 0.2910 is correct. 0.2899 is the last one. So if you take the average of all these three, you should get 0.2904. Okay. So I'm done with this. Now I'm going to store it out for our next time. Put the object in. So you know the procedure now, right? Reset. Doesn't look right. Okay. Huh? Oh, I think that's why you didn't do this. Okay. The height of this is 51.8. 51.8, so 0.518. And that's it. 0.3249 sounds right. Seems right. 0.3249. Point 3256. Oh, didn't work. Nope. Point 3262. How many did you get so far? 3?
Yeah.
Are they close enough? 3262, yeah. Point 3262. Is it like 0.3257? Huh? Like just 6? What's the next digit? Okay. So 0.3256 over here. And square it and put that number there.
One zero six zero two
0.10.
602.
That's it. We need only 4 sequence. So we can 4 sequence only. Alright, now my next height. 63.5. So 0.635. $63.5. Maybe wrong. I don't think it landed right. But anyway, write it down. 0.3603. Maybe wrong. I will tell you if it's wrong or right. Yes. 0.3603 is what I got, but I'll have to maybe remove that. 0.3603. But let's try again. No. 0.3603. Alright, didn't seem like landing properly, but anyway, 0.3603 again, there goes. So therefore it looks like it. One more time. 0.3591. 0.3591. So take the average of all this. So 0.3595. I don't know.
No, oh,
I'm
no,
looking
sorry.
at- I'm
I didn't know
looking
that
for-
last number you gave us. I thought you were saying 3595 for that
No,
last.
0.3591 is the last number. So the average is what I'm saying. 0.3595 is it? Right?
99.3599.
Oh yeah. Okay. 13599. That's right. Okay. And then square it. Put it down here. Let's go to the next and the last step. That's the other one. Nope.
What's the height?
I'll get it now.
Right.
Let's put it down. Point 76.4 76.3. 76.3. So 0.763 meters. Set. No. Point 3963. 0.3956. Now the last one. Good run. .3958. 0.3958. Is the average. And you want to required to get the last answer. Got it? You have the numbers, right? Alright, so we are trying to draw the graph. You know, Excel, I showed you last time, and I'm going to show you once again. On the table, above age, you know, age is going to be our y-axis, so just put y above the age, just as a reminder for us. And above the last column, t squared, put x, because that's going to be our x variable. Alright, so we're going to Excel. I told you column A is always the x variable, and column B is going to be the y variable, right? So column A is the x variable. So give me all the x variables right now, which is our last column, t squared. Go ahead. 0.0.
6703.
And then next one.
0.08433.
And next one.
0.1060.
Next.
0.1395.
Next.
0.1567.
Zero. What's the
1567.
1567?
Yes.
1567. And what's the next digit?
That's the last one.
Next digit is a 3.
Oh, so you squared it, right? This is square root. All right. Now the next one. That's going to be our y variable, which is our first column. Go ahead.
0.327.
0.327, 0.327. cell, on the first cell, drag it and select all of them. And after you select all of them, click on Insert, and then go to Charts, go to the first thing which says Scatter, click on the Scatter plot, and you have a line here. That line looks good. Don't see much of an error there. And you click on this and add the axis titles and the chart title. So the chart title is going to be our free fall. And our axis titles, the y-axis is going to be our height in meters. And our x-axis is going to be time squared. In second squared. And then what we have to do next is to right click on any of these dots. Right click on any of these dots. Go to trend, add trend line. Click on add trend line. Make sure that it's selected on linear. And you scroll down and click on display equation on chart. And so we have an equation right there displayed. That is our equation that we're trying to look for. Our slope. What's the slope? 4 point? 4.8458. That's going to be our slope. And we're going to use that. Now, look at the other number, 0.0054. That seems to be some kind of error that is crept in. Is it because of the height now? 0.0054 meters implies it is 5.4 millimeters. 5.4 millimeters is that much. So that much is possibly our error. That, I think, is possibly on the pressure pad. Because the pressure pad has a little pressure, right? It goes down a bit. So that could be it. That could be it. That's why the height difference comes in. But that's not significant at all. And that can also come in because of timing errors. You know, the timings were going up and down a little bit, so naturally you can get some kind of an intercept. So that's good. What do you do next? Right click on this, copy, and open up your Word document wherever you're working on it. Open your Word document. And then as you're doing the lab report, paste your Excel right there. That's it. That's all is needed. And after this will go under the calculations. The graph will go under the calculations. Yeah.
So when you right clicked and did the format trend line, how did you mind me go through that step again on Excel?
Okay.
What it was that you did, like you actually clicked on the format, that last.
Yeah. So let me remove this thing. So right click on this, any dot, format trend line, click on that, and then this thing opens up. Make sure that linear is clicked, and then you scroll down to the very bottom here, the second last line says display equation on chart. Click on that, and then your thing comes up like that. Now, so this is going to go under procedure, and observation is our table, and after the observation is the calculations. So this graph will go under the calculations because you are actually calculating the slope from the graph. So we got that. And after the calculations, what's our equation? Acceleration of the graph is 2 times the slope. That's all the calculations. So G is 2 times the slope. That's our very final equation, right? So what is 2 times 4.8458? Multiply 2 times 4.8458. What will you get? 9 point? 9.69 something meters per second squared. That seems good. Now, why is it not 9.8? First of all, it's not 9.8 in this area. It's only 9.77 or 9, something like that. So, why is it not 9.77 as it's supposed to be? What could be the source of error here other than the timing errors and all that? Any other error that you can see? Under precautions, you can actually add some of the things. Under conclusions, you can say what are the possible sources of error. Alright, so you're expecting to get an answer of 9.77, but you got 9.69. Yeah, 9.69, which is actually like a little lower. What could be the reason? Anyone?
Read the height now?
No, heights, mistake in reading the heights wouldn't have mattered because you're ultimately taking the slope, which is change in y over change in x. So when you say change in y, if there is an error made systematically, that will get knocked out. That is not the main thing. Any other source of error? Instead of acceleration due to gravity, 9.77, it only shows 9.69. What could be it? That also is not significant at all. I mean, those are mistakes.
How quickly you released it?
That can be a factor. You know, if there was a delay in the speed of release, then that can matter. Yes, that's one of them. Another factor is it's not falling freely. There's air, right? There's air. So as it is falling, air is trying to prevent it from actually picking up that acceleration of 9.7. So air is kind of acting against it. So if you're getting 9.69, that is reasonably fine. Especially when you're flying from a good height. As soon as it reaches here, air resistance is actually acting. So it actually is getting you more time than what is supposed to be there. Make sense? The time that you got there is a little more than what is supposed to be because air resistance is trying to impede its motion. So you can write your conclusions and precautions and all that. Any questions about this lab? All good? Any questions about this? There are no questions. We're going to the next one.